If you want to start a urea manufacturing plant, I've already given you the starting materials. Just go for it. So what's up guys, welcome to this channel. My name is Jeff. I am a chemist and a nuclear scientist. I'm affiliated to the University of Nairobi. And this is video 1 of the tutorial. We are going to start very quickly with chemistry. You know that chemistry is divided into 3 branches. We have physical chemistry, organic, and inorganic chemistry. So these 3 branches are related to each other in some way. We're going to pay close attention to organic chemistry because of its peculiar nature. Organic chemistry is very important in our daily lives due to its wide application. Now, so very quickly, we go to organic chemistry. Very interesting. Organic chemistry. Now, when you hear the word organic chemistry, the first thing that comes to your mind is what is chemistry in the first place. Now, chemistry is the study of composition, structure, composition, and transformation of matter. So you can add here study of structure, composition, and transformation of matter. Matter is anything that occupies space and has mass. So this object, anything that is composed of atoms and molecules and occupies space and has mass is called matter. Now, what is so special about organic chemistry? Organic chemistry is the study of carbon and its compounds. The study of carbon and its compounds. Now, one would want to ask, why would a whole branch of chemistry be dedicated to a single element in the periodic table? If you remember your periodic table, the periodic table is arranged in such a way that we have hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. We have sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon, potassium, and calcium. So these are the first 20 basic elements of the periodic table. And you will notice that there are 4 periods, 1, 2, 3, 4, and 7 groups, 8 groups, 1, 2, 3, 4, 5, 6, 7, 8. Now, carbon sits in group 4 of the periodic table, as you can see from here, with silicon. And this is very important from a chemist's point of view, because carbon reacts with 4 other. The fact that it's in group 4 means, and it is atomic number 6, means its electronic configuration is 2,4, and that means it reacts by bonding to 4 other atoms. This could be carbon, oxygen, nitrogen, sulfur, and so on. And so its Lewis configuration could be something like, assuming that is the nucleus and that is the first electronic, the first energy level, and this is the second energy level with 4 electrons. So carbon can bond to 4 other atoms, and this could be carbon, nitrogen, oxygen, and so on. So for this reason, there are over 9 million carbon compounds, and this represents 80% of all compounds, both natural and synthetic, that are known currently, because there are 12 million compounds. There are 12 million compounds, non-compounds, both natural and synthetic, and carbon compounds form 80% of this. So that's the reason why a whole branch of chemistry is dedicated only to one element in the periodic table. So then, now let's move quickly and see some of the areas we can apply organic chemistry in real life. Let me give you an example of compounds that we interact with that are important to organic chemists. Number one of these compounds is nicotine. Nicotine is found in tobacco. There are cigarettes sold everywhere in the world, people smoking, and most of them don't know what they are smoking. Now this is the structure of nicotine. So that is saturated with the nitrogen there. So this is nicotine, addictive alkaloid. So people who consume tobacco, who consume cigarettes, who smoke cigarettes, this is the complex organic structure they are consuming. Even though it is natural, it is addictive, and that's why it is difficult to stop smoking when you start. Don't start. Now the other compound that we interact with on a daily basis is vitamin C. We eat fruits to get vitamin C. Now this is what we get to fight diseases in our body. Now this is how vitamin C looks like. Let's just get some more space here, because it is a little bit more complex. So that is have a hydrogen there. And then we have cis configuration of two alcohol groups, and then you have that double bond there. So this is vitamin C. So when you hear about vitamin C that you get in fruits like oranges, this is the natural compound that is present in oranges. Now the other compound that is of interest perhaps is morphine. Now morphine is another compound So there's also stereochemistry here. There's some stereochemistry here. That thick bond connecting to nitrogen. So this compound here is called morphine, which is used as a pain reliever, as a painkiller, strong painkiller. What pharmaceutical chemists called analgesic. All painkillers are analgesics in pharmaceutical chemistry. So this is morphine that is used mainly in cancer treatment to relieve pain. It is a very important compound that's also addictive. That's why it is only prescribed for in very select cases, like in cancer treatment. So the other compound that perhaps you've tested, I don't know, is cocaine. Cocaine. Let's see. Let's come here and draw our cocaine. So cocaine will be drawn like that, like that, like that, like that, like that. Then you have that. Then you have that. You have a hydrogen there. Then we have a phenyl group here. which you can represent like this, saturated, and OH. So this is cocaine. Cocaine. So as you can see, there's something common in these addictive components, these addictive compounds. If you look at that, and look at that. So they have this group in common, a nitrogen attached to a methyl group that is common in all these compounds. So that's the magic of organic chemistry. It is applied in so many areas that we depend on it so much. And that's why 80% of all compounds in the world, non-compounds, are organic compounds. So that's why we need to look at this branch of chemistry with some sort of seriousness as chemists, as scientists for that matter. So one would want to ask, what is the relationship between organic chemistry and other branches of chemistry, like inorganic chemistry? So let me just talk about this to show you how organic and inorganic chemistry is related. Now initially it was believed that all organic compounds are natural, are produced through natural processes in plants. Like you've seen, all these compounds are natural products derived from plants. So that was the original belief, that all organic compounds were derived from natural processes. But then it became apparent when Frederick Waller, a German chemist, discovered that we can actually synthesize organic compounds from inorganic derivatives. And Frederick Waller discovered that if you hit ammonium cyanide, which is ammonium cyanide, which is an inorganic. This is an inorganic compound. You just subject it to heat, you form urea. Interesting, isn't it? You form urea. Amino group there and amino group there. Now this is urea, the fertilizer we use for top dressing. It is an organic compound. So it is this transformation from inorganic to organic that is of interest to chemists. That's why chemistry is the study of structure. You've seen the structures I've drawn here. It is the study of composition, what is it made of, and transformation. We have ammonium cyanide. This is ammonium cyanide. We just heat it. This is just heat, and we form urea. So if you want to start a urea plant, This is the process. Now let me show you how to get here. As you can see, we have cyanide and ammonium ion. So to get this derivative there, we can simply react ammonia. So if you want to start a urea manufacturing plant, just react ammonia with cyanic acid, which is so this is cyanic acid. So let me just write ammonia, cyanic acid, and then you form this NH4 positive O negative Cn. Now let me show you how we get this compound. So as you can see, ammonia has lone pairs of electrons, and this acid, there's a bond between hydrogen and oxygen to form this proton. So because this is a nucleophile, it will attack this proton like that, and this bond here will break and the electrons will be deposited. So initially we have 4 other electrons. So the electrons from this bond will be deposited on the oxygen to form an intermediate product that looks like that. Negative. So this one becomes negative, and because this one has been protonated, it becomes a positive NH4 ion. So it is Franklin Waller, this German chemist, who discovered that we can actually manufacture, not really manufacture, but synthesize ammonia, synthesize urea from ammonium cyanide. And that became a groundbreaking discovery. So most of the products, most of the compounds today are actually synthetic. All the drugs are synthesized from plants, whereas they exist, things like morphine, they exist in plants, yes, but how can we get them in proportions that we need to be useful to humans? So that's where organic synthesis comes in, which we'll look at in future in our subsequent tutorials. So I think we'll end there today for now. That was an inaugural tutorial of organic chemistry. Thank you for watching. If you like this content, please hit the like button below. Subscribe to this channel because more of this is coming. We are going to see very many areas. I told you we have 9 million organic compounds. We are going to see very many areas where organic chemistry is applied. We are going to see how all these processes take place. I told you, if you want to start a urea manufacturing plant, I've already given you the starting materials. Just go for it. See you there.